Good afternoon, everyone. Hopefully you can hear me. It doesn't look like you can right now. Well, maybe I am in and out. Welcome to TACO Tuesday. This is Brett Zerba with TACO. I already know you can see our screens because somebody responded to that, so that's good. Am I fitting out? Okay, no, people can hear me. Okay, great. Thanks, Thomas. Hopefully Rich will be able to hear. Well, today's presentation is on NPSH. Rich Medairos will be doing the main presenting. This presentation before, and it always brings up a lot of questions. So please ask the questions, or bring up some field examples if you have some. So I'm sure someone on this call, we have close to 150 people. Somebody's lived through some NPSH issues, and anyways, 24 hours from today, you'll get a copy of the recording and access to your PDH certificate. Most of you know the routine. I've seen some names I'm familiar with. Our good friend Tay is on. Out in Alaska. Good old Tay. Hopefully I'll be seeing him this summer. I haven't seen what day he's coming in. He's bringing some visit TACO. We have restarted our in-person TACO University classes. So if you're interested in coming to one of our classes, contact your TACO. Are the instrument to help you get to our facility. So that's enough introduction. Rich, take it away. Hello, Rich. We can't hear you. I think Rich is going to try to log back in.
I think we're having some technical difficulties, Brett.
I don't know why.
I don't know either. Let's.
I can hear you now, Rich.
Let's try sharing my screen and see what happens.
Yeah.
All right, I'm going to do a quick.
Your screen.
You can see my screen, okay? So I'm going to do a quick audio-visual test here.
And I'm hearing you loud and clear.
All right. So if the folks in the audience could wave their hand, let me know that you can hear me and see me okay. That would be a plus. I see lots of hands going up, so it sounds like I'm in good shape. You keep fading in and out, Brett, so I don't know if it's at your end or my end, to be honest with you. Because I cannot hear you now. So I tell you what we're going to do. I'm going to.
Well, take it away.
Let's try. I'm going to start and watch the questions, Brett, as they come in, and see if anybody's having trouble hearing me.
I just rebooted, working better.
Okay, so I got a message that says that it sounds like it might be a problem, Brett, at your end, but people can hear me. So I'm going to get started here, and if it turns out that you cannot hear me, then send Brett a message to the question system. I'll try that. So good afternoon, everyone, and welcome to TACO Tuesday. For those of you that have not met me, my name is Rich Medairos. I'm one of the senior systems engineers here at TACO, and my partner, Brett Zerba, and I do a lot of the commercial training for TACO. Today's topic is about net positive suction head, and it's a topic that people need to learn about if they're ever going to do any designs using pumps, specifically centrifugal pumps, which is where we have the greatest number of problems when it comes to net positive suction head. So let's see if this advances correctly here. I'm going to try my pen, by the way. Do a quick pen test here. All I'm going to do is draw a circle. Everybody can, well, I said that with, I'll draw a red circle. Everyone can see that circle okay. That would be great. Okay.
Looks good.
Looks good. All right, so what are we going to cover today? Well, I like to start off with what is net positive suction head. I like to mention the Goldilocks Planet, properties of water, how to find net positive suction head required, how to calculate net positive suction head available, and questions at the end. Now, this presentation is fairly short. We do get lots of questions, at least we have historically. So we try to allow for as many questions as possible. And as Brett mentioned earlier, hopefully you heard him okay. You don't have to wait to the end of the presentation. You can type in your question and Brett will ask me to pause periodically so that I will try to answer your questions. So Brett, do we have any questions before I advance the slides here?
No, sir.
All right, let's see what happens. So let's start with what is NPSH, and this is the formal definition. Net positive suction head. Net positive suction head for pumps can be defined as the difference between the liquid pressure at the pump suction and the liquid vapor pressure expressed in terms of height of liquid column. So that's the formal definition. It's the only slide that I will read today verbatim. You can take a picture of this slide. I'm going to leave it up for a few more seconds, or you can do a screen save, whatever technique you're using. And you can also, if you're going to collect the recording, which I think is going to be available roughly 24 hours from now, you'll have this definition in front of you. And then we have two other things. NPSHR stands for net positive suction head required by the pump, and NPSHA is the net positive suction head available from the system. So those are some definitions, and let's get on to some concepts here. So we live in what is known as the Goldilocks Planet, and astronomers refer to a Goldilocks Planet as a planet that is essentially not too hot and not too cold relative to liquid H2O, meaning that our planet is the right temperature and it turns out the right pressure to allow H2O to live or exist in a liquid format. And that's important because when it comes to pumping water, especially in an open system, and we're going to talk a little bit about what open means in a minute, it's important that since we're in the pumping business of pumping water specifically, which is a liquid, we want it to stay as a liquid. And when it changes and moves into the category of being a vapor, and pumps, specifically centrifugal pumps, do not like to pump vapor. They only like to pump liquids. So the Goldilocks Planet, as we know, is not too hot, it's not too cold. The atmospheric pressure is not too high and it's not too low. And that's where that term comes from, the Goldilocks Planet. All right, so how do we find the net positive suction head required by a pump? And actually, that's the simplest thing in the world to find, because all manufacturers that publish pump curve data or pump performance data include that in their pump curves. So here's a picture of one of our pump curves. And if you'll notice, right at the top here, it says required net positive suction head, NPSH. On the left-hand side, this is the units in feet, and what it actually is in feet of water column absolute. So this is absolute pressure over here. So if I could just use an example, I'm going to try grabbing a pen here. And let's see what happens. If I draw a vertical line, I'm just going to arbitrarily sort of pick one value here. I think this is, let's pick this one here. I think that's a roughly 2,300 gallons per minute. So if I draw a vertical line up, try to make a vertical line as good as I can, where it intersects this curve up here that's approximately, if I move on the left-hand side, 25 feet. So if I'm running this particular pump at roughly 2,300 gallons per minute, I draw a vertical line, and where it intersects this upper curve, excuse me, that's where it's going to intersect the net positive suction head required by the pump. So that's how you find the net positive suction head required by the pump. So it's as simple and straightforward as that. Brett, do we have any questions on how to find that requirement? And again, as I mentioned a moment ago, all manufacturers publish this data. I'm not hearing you, Brett, so I'm either assuming that we don't have any questions or you're still having problems with the audio here.
No questions, no
No
questions.
questions. Okay. Let's see if we can erase this stuff. This is always a challenge, erasing. Erase. Erase all ink. Hey, look at that. Whoa. Okay. Whoops, went too far ahead. All right, so this is a little reminder to switch me over to my whiteboard. So here's my whiteboard. Let's see if this works today, Brett. Little magic, wait for the background to take place. Whiteboard is loading. So we're gonna ask for a new whiteboard. Ta-da! Hey, we got a whiteboard. How exciting is that? Okay, so we're going to, let's see if we can get this pen to work here. We are going to draw an open container. Well, it's not the best container in the world, but you get the idea. Let's assume that I have an open container and it's open to the atmosphere. And it's partially filled with this famous liquid known as water. So there we have a partially filled container with water. And we will say that this is at sea level. I'm just going to write this up here so that we don't lose track of it. So this is at sea level. L-E-V-E-L. Ta-da. Okay. Did I spell level correct, Brent? Who knows? Okay, so I've got an open container. I'm at sea level. So the atmospheric pressure is 14 approximately. I won't use exact numbers today, but we'll go approximately. 14.7 pounds per square inch, PSIA, pounds per square inch absolute. Now let's assume that the water temperature of this, the water temperature is approximately 100 degrees Fahrenheit. Now I can get this water to boil by adding heat. So let's start, we'll add some heat here. I'm just gonna have a couple of arrows here, and I'll say I'm gonna add some heat over here. H-E-A-T. There we go. There's some heat. If I add heat to
Are
this,
you adding heat to boil some eggs?
I could boil some eggs, yeah. Do you want me to put some eggs in the water? No? You might want to, Brett, you might want to leave and then come back. You taught me how to do it. Because you keep breaking up and I can only hear half of what you're saying. Let me try this. Do you have any questions about adding heat yet? I don't hear you. Well, I'm going to keep going here. So we're going to add some heat to the water and we're going to raise the temperature, and I can't actually see anybody's questions right now, or if Brett hears anybody or sees anybody. We would have to raise the temperature at atmospheric pressure, which is around 14.7 pounds per square inch absolute. We'd have to raise that temperature to 212 degrees Fahrenheit, 212 degrees Fahrenheit, in order for that water to boil. So that's one way that we can get the water to boil. So when water boils, it forms these little bubbles like this. So we raise the temperature. There's another way that we can get that water to boil. Let's try something here. I just realized it's not going to let me erase a small part of this. Well, anyway, you learn something every day here. Another way that we can get this water to boil is that I could remove the heat. So I'm going to X out this heat right here. The water is at 100 degrees Fahrenheit. So I'm not going to raise the temperature, but what I will do is I will cover this container so that it's sealed from the atmosphere. And I will put in an imaginary vacuum pump over here. Let's just have this imaginary vacuum pump. And I'll just put VP for vacuum pump. And I'm going to evacuate this container. So it's now sealed from the atmosphere. I'm going to evacuate the container, and I'm going to reduce the pressure in here until it gets down to 0.94, 924 PSIA. So I've reduced that pressure. So if I put a pressure gauge over here, and this pressure gauge read in absolute pressure, it would now read 0.94924 PSIA. So we'll put that right in there, PSIA, pounds per square inch absolute. And if I can reduce the pressure to 0.94924 pounds per square inch absolute, that water will begin to boil at 100 degrees Fahrenheit. So this temperature, I have not changed the temperature in the second scenario here. All I did was reduce the pressure. That will cause the water to boil. So as far as using my whiteboard, I just wanted to demonstrate that there are two ways you can get water to boil. You can either raise the temperature or leave it at its initial temperature, in our case 100 degrees Fahrenheit, and reduce the pressure. If I can reduce the pressure low enough, the water will boil. So do we have any questions out there regarding the water boiling and the concept between pressure and temperature? Look quickly here to see if there are any questions out there. Okay, I don't see any new questions regarding the diagram that I put together. Okay, so let's try moving right along, as they say. We'll go back to our, get rid of our little diagram here and erase this stuff. There we go. And we'll go back to the PowerPoint. Okay, so where did I get that pressure from? Well, it turns out you can get that pressure from what is known as tables of properties of saturated steam. And this shows us the relationship between the vapor pressure and the temperature. So if I scroll, whoops, if I go to the next page, you'll see that at 100 degrees Fahrenheit, the first column is the vapor pressure. In this case, it's the number I just told you, 0.94924 pounds per square inch absolute. So let me just go back to that previous page. So the first column is temperature and the second column is absolute pressure. And so you can see at 100 degrees Fahrenheit, if I can reduce the pressure to this value, the water will begin to boil. So that's where you get the information regarding the vapor pressure. All right, so let's go on and see, how do we actually calculate?
Hey, Rich, can you hear me?
I can hear you now. Go ahead, Brett. No.
There's a question. It's from John. It says, is boiling of the water the same thing as cavitation?
Ah, that's a great question. It turns out that when we have water that's entering a pump, let me go back to my whiteboard here. Try this one more time. Come on, Mr. Whiteboard. Well, this is a strange day for technology. This is not the best technology day I've seen in a long time. All right, so there's our whiteboard. So what happens, let's do this. Let's draw an impeller in cross section. Here's an impeller.
I guess.
Okay. And let's say the water is entering that impeller from left to right. And let's say that the pressure at the inlet of the impeller, that's the lowest possible pressure. So I'll put an L next to that. And then on the discharge of the impeller, I'll put an H for high pressure. And it turns out that in our case, we said the water temperature was about 100 degrees Fahrenheit. So I'll put that in here too. 100 degrees Fahrenheit. I don't know why that has a little leg on it, but well, let me try erasing that little tiny piece there. Yeah, and we go back here. And that's 100 degrees Fahrenheit. Well, if the pressure is low enough, in our case, we said it was 0.94924, and that's, again, pounds per square inch, 94924, pounds per square inch absolute. So we'll label that PSIA. So if the pressure gets low enough, that water, as it enters the eye of the impeller, will begin to boil or create bubbles. See that? And then as the water flows from the inlet to the outlet, the pressure increases. And when the pressure increases, those bubbles begin to collapse. And the phenomenon of cavitation are the collapsing bubbles that take place as they pass through the impeller. So hopefully that answered that question, Brett.
I bet you it did, Rich. I bet you it did.
I think it did. Okay, so we are going to try transitioning back to our PowerPoint presentation here. Technology is a wonderful thing when it works. It's very disappointing when it doesn't work. Okay, so what we need to do is we need to figure out what is the net positive suction head available at the pump inlet. So we have a little diagram here. Let me explain the diagram. Grab my pen over here. We have a little diagram. Here we have a cooling tower that's open to the atmosphere. That means, and we're going to assume, like we did earlier, that I'll just have the abbreviations here, that we are at sea level. I'll just put in SL for sea level, which means that our atmospheric pressure is approximately 14.7 here. And again, that's PSIA, and that's our atmospheric pressure. So in order to figure out what the net positive suction head is available, that's this definition up here. Net positive suction head is available at the pump suction. We have to use this formula right here. And if you'll notice, the formula, it says that it's the atmospheric pressure, in our case 14.7 pounds per square inch absolute. If I converted that into feet, if you recall, it's approximately 2.31 feet per PSI, So that's the conversion between pounds per square inch and feet of water column. So the atmospheric pressure is approximately 14.7, that's this value here. And if I multiply that by 2.31, that'll be approximately 33.9 feet. The next number in the equation is the vertical distance, and that's this distance between the water level in the cooling tower and the center line of the pump. In this case, the pump is below the water level in the cooling tower, and the distance is approximately 5 feet. That's that little 5-foot mark right there. And so that, and it's a positive value, plus 5 feet, because the water in the basin of the tower is above the center line of the pump. If the water level in the basin of the cooling tower was below the center line of the pump, then the vertical distance would be minus. That's why there's a plus minus over here in the formula. Now, we do not recommend that for an open system that you put the cooling tower below the center line of the pump. But it's important to recognize that the vertical distance is either a positive value, and that's when the pump is below the cooling tower, or a negative value when the pump is above. And again, we don't recommend that you do that. The next value here is the pressure drop or the friction value. And so that would be a normal calculation where you calculate the pressure drop in the piping system, including all the fittings like elbows over here, end suction diffusers, all the components between the cooling tower and the suction side of the pump would be the friction value. The next value is called the velocity pressure. And velocity pressure is fairly simple. So I'm going to put V sub P right here, velocity pressure. And this comes from Bernoulli's equation, if you need a reference for this. So the velocity pressure is equal to the velocity squared divided by 2 times the gravitational constant. And let's see, yep, 2 times the gravitational constant. And if we're talking about inch-pound units or imperial units, the velocity is going to be in feet per second. I'm just going to make an arbitrary velocity here for a moment. You kind of see where I'm going with. So if I say that the velocity is 8 feet per second, FPS, 8 feet per second, I need to square that value. So I'll put that in parentheses, 8 feet per second squared, divided by, this is equal, by the way. That's divided by 2 times the gravitational constant, and in imperial units or IP units, the gravitational constant, that means times right there. It's not the best time symbol, is it, Brett? Is 32.2 feet per second squared.
Nope.
I can't squeeze in that value, but I'm going to put it in pretty close here. 32.2 feet per second squared. So if I multiply the denominator by 2, 32.2 times 2, that's 64.4, and 8 squared is 64. So the velocity pressure in this example, I'm going to write that over here on the left a little bit. It's approximately, it's not exactly, but it's approximately equal to 1. And that the units for that are feet. And again, this is feet of water column absolute. So this is absolute pressure. So in our formula, the velocity pressure is always equal to V squared divided by 2G. And if you're in imperial units, you're dividing by 2 times 32.2. And if your velocity is approximately 8 feet per second, you're going to find out that your velocity pressure is approximately equal to 1 foot. So that's where that value comes from. And the last value in the equation is the vapor pressure, which we got from the steam tables. And in our case, we said it was 0.94924, but that's in pounds per square inch absolute. So if I multiply 94924, let's see if I can do it over here, 924 times 2.31, that's going to come out to approximately 2.2. And that's going to be, I'll draw an equal sign, vertical equal sign with an arrow on it. That's going to be approximately 2.2. So that's where all the numbers came from. And that, again, is in feet. And that's where all those numbers came from in that formula. So, Brett, do we have any questions about the formula or where all the values came from? Since I can't hear you, apologize to everyone out there.
Well, Rich, hopefully.
There are a couple of questions. I don't know if you can hear me or not.
I can hear you now. Go ahead.
All right, so Mario Silva asked.
Well, actually, let me see here. What have we got for questions? Well, so Brett, you're breaking up, but I can see the question. Mario's question was, do the bubbles implode or explode? And when the bubbles first form in the eye of the impeller and they pass through the impeller to the high pressure side, they implode or collapse. And those collapsing bubbles is the phenomenon known as cavitation. And then we have another question from Kevin. Is the required net positive suction head on the pump curve for a specific temperature? No, the net positive suction head required by the pump is temperature, is not temperature dependent. It's actually the amount of pressure above the vapor pressure. The vapor pressure that you look up in the steam tables is temperature dependent. So we have another question from John. The net positive suction head available equation in the reference material for the PE exam excludes the velocity pressure term. And the reason that a lot of people exclude the velocity pressure is because, generally speaking, it's a very, very low value. So I just showed you an example of 8 feet per second. We generally recommend for open systems, when it comes to, in this case, it's a cooling tower, we generally recommend that your entrance velocity to the pump be less than 8 feet per second. And we generally recommend that you want to be somewhere around 6 feet per second. So at 6 feet per second, it's going to be lower than 1. So it becomes a very, very small value. So a lot of people leave it out. What you do have to take into consideration, however, is that if you have an unusual condition of a very high velocity, you do have to calculate the velocity pressure, because sometimes that can make a difference. But most people will design open systems, especially when it comes to cooling towers, at a relatively low velocity at the entering condition of the pump. And usually it's negligible and they leave it out. So that's the reasoning behind there. Then it says, if the water temperature is different than the ambient temperature, is ambient temperature used rather than the water temperature? No, you always use the water temperature, not the ambient temperature. So whatever the water temperature is at the suction side of the pump, that's the temperature that you use. So hopefully that answers the current set of questions. All right, so I'm going to erase everything on the screen here. I'll try erasing all of that. And when I do that, ta-da, I'm going to go to the next slide. Excuse me, we're going to substitute some real values in here. Go to the next slide, and you can see that the formula net positive suction head available, again, is 33.9 feet. That's the atmospheric pressure converted into feet. The pressure drop is estimated at 5 feet. So when we did the pressure drop calculation between the water that's in the sump to the suction side of the impeller, the vertical distance is 5 feet. So we add the 5 feet. Ooh, I think I did that backwards. The first value is the vertical distance. The second value is happens to be the same value. That is the pressure drop, is estimated at 5 feet. The velocity pressure, I'm using 10 feet per second for this example. And so if you take 10 squared divided by 64.4, it comes out to approximately 1.6 feet. And as we said before, the vapor pressure is approximately 2.2 feet at 100 degrees Fahrenheit. So if you do the arithmetic, those values come out to approximately 30 feet. And I have selected a pump that has a required net positive suction head of 18 feet. I always like to be at least 10 feet below the available pressure when I select my pump. Or I can say that in reverse. If I have a pump that has 18 feet, I want to make sure that I have at least 10 feet more than that available before I make my selection. So we got a couple of more questions here. Let's see how we're doing for time. We're doing actually very good for time. Let's see. There are guidelines that talk about feet of straight pipe at the entrance to the pump. For instance, and I'm not sure what this NNFP wants 10 feet of straight pipe for fire pumps. Oh, okay. So that's the, what is that? NNFP, is that the National Fire Protection Code? So Bill is telling me that. So Bill, if you want to help us understand what NNFP stands for. Okay, pumps other than 5 feet. So when it comes to, we do not manufacture fire pumps. So if you're quoting something from the fire pump regulations, I have to tell you, we don't have a lot of expertise when it comes to fire pumps. But in general, the smoother and the less pressure drop that you have at the inlet of a pump, the less problems you're going to have with respect to net positive suction head. But again, if the available pressure is at least 10 feet above what's required by the pump, then you shouldn't have a problem with cavitation. Oh, here's a question here. How hot can the water get? Well, we've been talking about open systems, and so I'm not initially talking about hot water heating systems. But if you had a hot water heating system, you would do the same exact calculation. It could be a closed loop system, and you'd look at the pressure at the inlet of the pump with respect to a closed loop system. And generally, the pressure at the inlet of the pump is going to be controlled by the expansion tank. And so you could have normal hot water heating system temperatures and pressures, say between 180 and 200 degrees Fahrenheit. I shouldn't use the word normal. I should say most systems are designed between 180 and 200. If it's a high temperature, high pressure system, that's a special case. But the calculation is the same, but instead of starting with the atmospheric pressure, you start off with the pressure at the suction of the pump, and generally that's the minimum pressure in the system controlled by the expansion tank. We got another question here. It says, okay, it says, how hot can the open system water get and still meet the net positive suction head available? Well, again, when you look at the steam tables, you will see that when you start getting close to 212 degrees, the water will begin to boil. So what you have to make sure of is that if you have a relatively high temperature, you have to have a relatively high static pressure at the inlet of the pump to keep it from cavitating. Okay. Let me just, let's see what we've got here. Hold on one second. This, I wanted to show you a picture of what an impeller looks like when it cavitates. And so here's an impeller that is it is completely destroyed by cavitation. You can see it looks like somebody bombarded it with sand particles. And it'll destroy an impeller in a relatively short period of time if the pump is cavitating. And in some cases, it can also destroy the volute. But generally speaking, it will destroy the impeller first and then the volute second. So we have a few other questions that popped up. See if we can answer them. How you doing out there, Brett? I haven't heard your voice, so I'm not sure if your system is still working. I'm hoping people can still hear me. So in the question area, if someone could just type in, they can still hear me okay? Someone said okay. All right. Let me try to read a couple more questions here. It says, city pressure for domestic hot water is typically 60 pounds. How is that incorporated?
Test.
You're back, Brett. Go ahead.
You can hear me now?
I can hear you now, yes.
That's all right. Yeah, okay. Well, I'll keep trying.
Go ahead. Did you want to read a couple of these questions? No, we're still having technical difficulty, Brett, with your sound.
I've been trying a lot of things, Rich. It's just not working today.
Yeah, I understand. Let me try to answer Tay's question. Tay's question is city pressure for domestic hot water is typically 60 pounds. How is that incorporated into the NPSH calculation? Well, when you say city pressure, that generally refers to the pressure that's entering the building. And when we talk about domestic hot water, if there is a pump on the domestic hot water system, for example, there might be a recirculating pump, we have to calculate what the actual pressure is going to be at the inlet of the pump from the source, in this case, might be city water source. So if the pressure entering the building is 60 pounds, and let's just assume for a moment that the pressure drop from the building entrance to the suction side of the pump, I'm just going to make up a number, and let's say that's 10 pounds, then that means that the suction pressure at the pump is going to be equal to roughly 50 pounds. Now that's pounds per square inch gauge, so you have to convert that into pounds per square inch absolute by adding 14.7 PSI to convert it into absolute pressure, and then to convert it into feet, multiply that by 2.31, and that would be the actual or the available pressure, the net positive suction head available using that calculation method. Now you compare that value with what's required by the pump. So generally speaking, you always have to be careful when you use the word general. Generally speaking, when you have a pressurized system, you usually have more than enough pressure than what's required by the pump, even if it's a hot water system. Okay. Is the pressure shown in pressure gauge at the suction of the pump, the net positive suction head, available? Well, there is one value that you have to do a couple of things. First of all, whatever you're reading in a pressure gauge, you have to convert it both into absolute pressure. So let's assume that you had a pressure on the suction side of the pump and you were reading a gauge pressure of 20 pounds. You'd have to add 14.7 so that its absolute pressure is 34.7. And then you have to multiply that by 2.31 to convert that into feet. So that would be 80.15 roughly feet. And if the pump requires, say, 10 feet, then you would have an available pressure that's greater than what's required by the pump. Now you do have to correct for velocity pressure. So you'd have to subtract from the gauge pressure, the velocity pressure. And that would be the velocity at the point that you were taking the pressure reading. So hopefully that answers that question. Okay, the next question is it best to keep pumps in the basement instead of the penthouse to avoid cavitation issues? Well, when you're talking about an open system, for example, a condenser water system, generally speaking, in terms of vertical distance, the greater the vertical distance between the open part of the system, which in this case could be a condenser water cooling tower, and the location of the pump, then the greater the available net positive suction head available pressure would be. So in general, generally speaking, if we can put the pumps in an open system in a basement and we can put the cooling tower on the roof, that is the preferred orientation. But we don't always have that luxury. So we have to be very careful as to where we put the tower and where we put the pump so that we have as much pressure available as possible to keep the pump from cavitating. Okay. So I've covered, let me make sure I've covered all the material I wanted to cover today. Hold on one second. Yes.
Let me just say this, Rich.
Go ahead, Brett. No, Brett, unfortunately, Brett, you keep jumping in and out here. Okay, so someone asked, is adding 14.7 psi to the inlet gauge pressure also required in a closed loop system? And the answer is yes. And the reason for that, you always have to convert it into absolute pressure and then multiply by 2.31 if you're taking the pressure readings in psi, is because the net positive suction head required by the pump is published in feet of water column absolute. So you always have to make that conversion. All right, do we have any last minute questions out there?
Hey, Rich.
Yes. Unfortunately, Brett, I heard you say, hey, Rich, but I didn't hear you say anything.
That picture of that impeller, that's
No, Brett's jumping in and out. Let me try answering a couple more of these questions. Is it required to consider NPSH available in the closed loop system? And the answer is yes. And so let me give you an example. If you have a closed loop system, and let's assume it's for hot water, and I'm just going to arbitrarily say it's at 200 degrees Fahrenheit, and your pump is at the very, very highest part of the building. So maybe, let's say you had a 10-story building and you had a mechanical penthouse at the top. The pressure at the very, very top could potentially be quite low. And because the temperature is relatively high, you should do the calculation with respect to the net positive suction head available, because remember, the vapor pressure is going to have a significant impact on the available pressure with respect to the absolute pressure. So you should do the calculation. You should always do the calculation, but especially when you have either relatively hot water, the pump is at the top of the building, or you have an open system. Generally speaking, if it's a chilled water system, for example, it's a closed loop pressurized system, and then the pump is at the bottom of the building, usually have enough pressure in the system to avoid the pump cavitating. A couple of other quick questions here. Let me see. Does the 14.7 PSIA have to be adjusted based on elevation? Yes. Oh, that's a great question. And when we talk about elevation, we're talking about relative to sea level, which is why in the examples that I kept giving you was all about sea level. So as you go up, if you're in a place that's higher than sea level, for example, Denver, Colorado is considered to be the mile-high city because that's a little over 5,000 feet above sea level. And so the atmospheric pressure is lower. So you have to look at the atmospheric pressure tables as they pertain to elevation changes. So that's one of the things that we ask. Many times someone will call me up and they'll say, I have an issue. It sounds like the pump is cavitating. It's an open cell system. It's an open system rather with an open cell cooling tower. And I seem to be having a cavitation problem. And I'll say, well, where are you in terms of the country? And they say, oh, I'm out in Denver, Colorado. And I said, well, did you correct for the change in elevation? No, I didn't. I looked up the information based on the sea level data and said, well, maybe if you adjust your calculation accordingly, you'll see that it could be a problem. All right, we have time. Let me see how we're doing for time here. We're actually doing quite well for time. Another question is, are we always designing NPSH available to be approximately 10 feet above the net positive suction head required? Well, I like to use 10 feet because I'm a bit conservative, and I know from experience that if I have the available pressure 10 feet above what's required, then I won't have a cavitation problem. Now, some engineers will design their system to be within 5 feet. The challenge there is that there is always fluctuations in water levels, especially in an open system. And so I like to be conservative and use 10 feet. So I have seen designs where people will use a value 5 feet, but it all depends on what kind of safety margin do you have. All right, so another question that popped up, what happens if there is no minimum straight pipe distance in the pump suction? Does it cause cavitation? Remember, cavitation, again, is a function of the pressure and temperature of the water as it enters the impeller suction. So anything that affects the inlet pressure at the pump is ultimately going to affect the available pressure. So I think the answer to the question is that you don't absolutely have to have a straight run of pipe, but you do have to do the calculation and account for the pressure drop if you're not using a straight run of, well, actually you have to calculate the pressure drop regardless of the pipe configuration or the entrance conditions of the pump. So you always have to do the calculation. What I would then say is that if you had a straight run of pipe, say 10 pipe diameters at the suction side of the pump, your pressure drop in that region is probably going to be negligible as compared to if you had an elbow, for example, a short radius elbow at the pump suction, or if you had an end suction diffuser, you'd have to account for the pressure drop of those components, which would be greater than a straight run of pipe. Okay, and then it says, is there a problem with, if there is a problem.
Getting a lot of questions now.
Yeah, we are. These are cool questions. If there is a problem with NPSH, can you please advise, is there a solution? Well, again, if you go back to the calculation that we did, actually, let me put that up on the screen. Let me try that. Let's see what happens here if I do that. Yes, here's the little diagram that we had from before. And so let's assume for a moment that the calculation came out to be, well, let's say the calculation is correct at 30 feet, and the pump that was installed, let's say it's an installed situation, and the pump that was installed was, say, 32 feet, the required NPSH. So now we have a problem where the installation, the required pressure is greater than the available pressure. Let me say that in reverse. The available pressure is less than what's required by the pump. In that case, what can we do for solution? Well, there are multiple things that you can consider doing. Going back to the equation, let's see what's influencing the available pressure. We can't change the atmospheric pressure. Atmospheric pressure is whatever it is in an open system wherever you are in the world. Can't change that. But you could potentially change, let me grab my pen here for a second. You could potentially increase the height. You could move the cooling tower up. You could increase the height of the cooling tower. Again, let's assume for a moment that our required NPSH was 30, I'm just going to make up a number here. Let's say it was 35 feet. That was what was required by the pump, and the calculation indicated that you only had 30.1 feet, approximately 30 feet. So now we have the available pressure is less than what's required, so you could raise the cooling tower. Well, that could be expensive. Another option is to lower the pump, and that might be less expensive. And you say, well, how can you lower the pump? Well, if you consider, let's assume that this is the ground level here. I'm just going to extend that. You could put in a vertical turbine pump, but you would have to have a special well or something like that. A vertical turbine pump allows you to reduce the suction elevation. So let's assume that the suction of the vertical turbine pump was way down here, and I'm just going to arbitrarily make that distance. Say I'm going to say that's 20 feet, kind of drawing like this. If I put in a vertical turbine pump that's 20 feet below my other pump, then effectively I have increased my available pressure by 20 feet. So if my original calculation was 30 feet and I put in a vertical turbine pump whose suction is 20 feet below that, I could add that 20 to the 30 and I have 50, and now I have 15 feet above what's required by the pump. Another option is to increase the pipe size on the suction side of the pump to reduce the pressure drop. And then if you have the physical distance, and this is where it gets a little complicated, but if you had the physical distance, you might consider having, if your piping is overhead and it comes down, if you could put a long radius elbow in there and then get rid of the end suction diffuser, then you could decrease the pressure drop. Because remember, this equation right here, you don't have any control over the atmospheric pressure, but you do have control over the vertical height, you have control over the pressure drop. You don't have any control over the, you do have rather control over the velocity pressure, because you could change out the pump. The pump that let's assume we selected a pump that had 35 feet, and what was available again was 30 feet. Maybe I could change out the pump and put in a pump that had a requirement of only 10 feet, and maybe that would do the job, that sort of thing. So hopefully I helped answer some of those questions.
You're getting a lot now.
I'm getting lots of cool questions here.
Yeah.
Let's see. Let me skip down to, I hope I pronounced this correctly. If I'm not, please tell me. Is it Carmine? Carmine asks, comment, 10 feet safety allows for dirty strainer. Well, when I do the calculation, I always look at the characteristics of the strainer, and I take the pressure drop of the dirty strainer as opposed to a clean strainer when I do my calculation. So it's one of those things where you have to think about, when you do the pressure drop calculation, what parameters are using for each component in the system. So if I'm doing the calculation based on a dirty strainer, and if my available pressure is marginal, then I would modify my design in some way so that I could allow for a dirty strainer and still have sufficient pressure to keep the pump from cavitating. All right, so another question here says, reducing temperature, increasing system pressure, and slowing pump flow can all help. Yes. Brian has made a statement, and I agree with Brian. If you can reduce the temperature, increase the system pressure, and slow the pump flow, all of that can help. But sometimes you don't have control over certain things. For example, in many designs, the cooling tower entering water condition might be, for example, a maximum of 100 degrees Fahrenheit. And maybe that's the way the cooling tower was sized, in which case you can't reduce that temperature. But sometimes you can. So one of the things that I always try to talk about is that there's a difference between after the installation and then during the design. If you have calculations that indicates that you potentially could have a problem, it's much easier to solve it on paper before you try to solve it in the field. So take that into consideration.
So Rich.
Yes, I can hear you, Brett.
Yeah. I don't know for how long, but this is an interesting question. Alexander is asking, for a closed system, what is defined as suction piping versus discharge piping? So he's probably referring to the plus and minus the, in the drawing, the sketch you're showing, you're showing that suction piping coming from the cooling tower down into the pump.
Yeah, so the suction piping in this, what we're referencing here is this piping right here, if I can kind of circle it, including the suction diffuser, if there happens to be one. That would be all the suction piping. When it comes to net positive suction head calculations, you're only concerned about the piping on the suction side of the pump. This piping over here on the discharge side does not enter into the calculation.
What about in a closed loop system? How far back do you go?
Well, in a closed loop system,
you know what I mean?
Typically, let's make a little tiny sketch over here. Let's say we have a pump, and that pump is pumping water throughout a system. Let's just say it goes out here to Never Never Land, and eventually that water comes back from the system. Maybe it goes into a boiler. This is a closed loop system now. And maybe it exits the boiler, coming back here. It exits the boiler and goes into the pump. Well, we recommend for closed systems, so this is kind of going out to the system here, and this is coming back from the system. So in a closed loop system, we recommend that the expansion tank be placed on the suction side of the pump, and this connection here is known as the point of no pressure change. And if you select your expansion tank properly for the static height in the building, maybe that static pressure, or the minimum pressure rather, I'm just going to make up a number here, is let's say is 50 pounds, 50 psi G. Because when it comes to expansion tanks, we generally think in terms of PSIG. When it comes to net positive suction head, it's in feet of water column absolute. So if my expansion tank, ET, is there, yeah, I guess it is. Okay, so let's say that the minimum pressure in the system is 50 pounds. I would convert that into absolute by adding 14.7, so that'd be 64.7 times 2.31, and that's the absolute pressure. Now I can compare that against what's required by the pump. So in a pressurized system, it's the expansion tank connected to the suction side of the pump, which is the point of no pressure change that we use as the inlet side. Now, we have to be careful because the connection point here for the expansion tank has to be very close to the suction side of the pump. If you put the expansion tank 400 feet away at a different elevation, then you can't use that as the pressure at the suction side of the pump. How are we doing, Brett? Any more questions?
I think we've run amok. I think we've covered most of them, so we're in good shape.
Well, let's see. Someone did ask the last question here. It says, relative to friction loss, is it the whole system? When it comes to a closed loop pressurized system, we're only interested in what the pressure is at the suction side of the pump, as I've indicated here. And generally that's controlled by the expansion tank in a properly designed system. So Brett, that's about all I have for today. And look, we got lots of questions, so I'm glad that
Yep.
we had lots of participation, and hopefully we've answered nearly everyone's question. I'll erase all this stuff here.
You know, NPSH is just a subject that it shouldn't be so critical, but it is, because when there's an issue with it, all hell breaks loose. That's for sure. And the calls we get sometimes, usually it's not on a 5 horsepower pump. It's on a 50 or 100 horsepower pump, right, Rich? It's not small one.
You're absolutely right. I mean, usually, usually what happens is if somebody calls up and says, "Well, I've got a 2 horsepower pump and it's cavitating," and I'll say, "Well, what's required by the pump and what's available?" And they say, "Well, 10 feet's available, and the pump is requires 10 feet." And I said, "Well, that's too close. We can make a selection for a pump perhaps that requires 5 feet, and that'll give you some safety margin. But to replace a pump that's 2 horsepower to go from 10 feet to 5 feet is not a big expense. But as you've already pointed out, Brett, if it's 500 horsepower, that's when your day gets ruined."
Yeah, you know, and most of the
You're breaking up, Brett. I'm sorry, but can't hear you anymore. Dead airspace. All right, so here's what I'm going
at
to
one
do.
point in their career are going to be responsible. Okay. Damn it.
Yeah,
Sorry.
I think we're going to have to cut it at this point, Brett. We're going to have to figure out the technology here, what's going on.
Yep.
But I'm going to say goodbye to everyone. Thank you so much for participating. I apologize that we're having some technical difficulties. Hopefully you could hear me and most of your questions have been answered. If you do have some additional questions, don't hesitate to contact your local rep. They should be able to answer your questions. If it's a question that they cannot answer, they're more than happy to give Brett and I a call, and we'll do our best to answer the question. So I'm going to sign off for now and say thank you very much, and thanks for participating. Take care, folks.